8.6 confidence intervals. So in everyday life, different people use confidence intervals. Okay, an example of this is when governments commission polls to gauge support for new initiatives. Okay, so what this means is like organizations are hired to call people, and they call a small number of people, and what they do is they ask maybe who someone's voting for or if they support a new initiative, whatever it is. Okay, and what they use is that small number of responses in order to estimate support for the entire population. Okay, many of the polls state something that looks like this, plus or minus 3%. What that means is that so up 3% or down 3%, than what they what like the average is or what they think. Okay, and then it'll say like something like 19 times out of 20. So of course if we take 19 and we divide it by 20, we know that that's 95%. Okay, so what this means is that there's a 3% error, either error above or error below the data set, with a confidence level of 95%. So the probability for error is 1 minus, maybe you want to put this in brackets, the confidence. In other words, 1 minus 0.95. So the confidence is 5%. Okay, here's an example. If a poll states that 43% of people support a certain government, accurate within plus or minus 3%, 19 times out of 20, what this means is that there's a 95% probability that between 40 and 46% of the population supports the government. And therefore, there's a 5% probability of error. That 40 and that 46, they just come from taking 43 and going up 3, so adding 3, making it 46, or subtracting 3, which makes it 40. Okay, so between those two numbers. Okay, so here's a couple points on confidence intervals. Range of values where the population mean, which is mu, is likely to fall. Okay, that's what a confidence interval is. Okay, a range of values. Okay, when we see confidence interval, take a look right down here. I'm just going to show you. See the mu? So mu is between this number and this number right here. That's what it means. And intervals are centered on the sample mean. Okay, that's where this comes from. We take the sample mean and we do plus or minus. So minus, say the 3%, and then we'll take the sample mean and we'll plus the 3%. And we'll base our population mu, the mean for the population, on those two intervals. Okay, so formula is based on the sample mean x bar, the population standard deviation sigma, and the sample size n. Okay, typical confidence intervals, what we're going to see in these questions are 90%, 95, and 99. Okay, those are the most common. Example, a 95% confidence interval has a 0.95 probability of including mu. Okay, in general, the range of values is represented by this range right here. Keep this equation in mind when we go ahead and compute. Okay, so for confidence levels, 9 times out of 10, 19 times out of 20, or 99 times out of 100, we saw these are the 3 confidence intervals that we're going to use the most. They're the most popular. Okay, what happens here is that we're given some, like think of it as like a bell curve, and we're given some mu, and then we have confidence that 95% of the time it's going to be within maybe, say that minus 3% and then that plus 3%. Okay, when we talk about tail size, what happens is these two tails right here and here, okay, the 10% left over is going to be divided into this tail and this tail. Okay, so it would be like 5% and 5%. Okay, out of the 95%, again, the tail size is whatever's left over divided by 2. Okay, because we're going to divide it equally into the 2 tails. So 5% is going to be divided by So when we take the 5%, we divide it into these two tails, we get 2.5% each, right? And that's what this means. Okay, and again, 99 times out of 100 is 1% divided into the two tails, which is 0.5%. Okay, the corresponding z-scores. So if we were to look these numbers up right here on the z chart, these would be the z-scores that correspond to them. Okay, so we're just going to take a note of these and we're just going to use them straight off of this sheet. So let's move to example 1. Okay, drying times. Paint manufacturer knows that the paint that he sells has a standard deviation of sigma equals 10.5 minutes. Okay, sigma equals 10.5 minutes. Okay, 20 test areas of equal size, so 20 test areas, that's the sample that we're taking, are painted, and the mean drying time, x bar, is found to be 75.4 minutes. Okay, find a 95% confidence interval level for the actual mean drying time of the paint. So if we refer back to the equation that we have, what we have is x bar minus z, like the z value from the chart of one of the tails, sigma over root n, okay? And mu has to lie between that and then, so x bar minus and then x bar plus. Okay, the z value of one of the tails, okay, sigma over root n. So we can go ahead and just sub these values in. And for 95%, we're going to sub in out of that chart 1.960. Okay, so x bar, I get 75. I'm actually going to write it like this, plus or minus, 0.4, plus or minus the z-score, which is 1.960, times sigma, 10.5, over root n. Okay, and once you do that on your calculator, plug everything in, you are going to get 70.8 for the minus side, and you are going to get 80 for the plus side. So what we can conclude here is, and I'm going to actually type this, I like to take this more. Okay, we can say he, one up there, he can be 95% confident that the actual mean drying time for the paint is between 70.8 minutes and 80 minutes. Okay, so if the paint had an advertisement on it saying will dry in 80 minutes, okay, dries in 80 mins, then that would be very reasonable. Okay, now we're going to talk about sample sizes and margin of error. So what we're going to do is we're going to work backwards. Sometimes we'll be given an interval width or margin of error. So that's what is called plus or minus, right? Like margin of error. And we're going to look to calculate the minimum sample size necessary to achieve that margin of error. So in this, we must solve for the sample size n. Okay, this is the equation right here for n. And this will give the people conducting the poll the number necessary to sample in order to achieve that specific margin of error. So for example, going back to that government example, if you wanted to have a 95% confidence that plus or minus 2, or plus or minus 2 people, or plus or minus 2%, what you would have to do is you'd have to be like, okay, how many people do we have to actually sample in order to achieve that? So this is what we are going to take a look at. Sample size for quality control testing. Suppose the diameters of bolts, so you guys know what a bolt is, maybe it goes like this. Okay, used in assembly of a fridge have a standard deviation of 0.1. Okay, how large of a sample? So when you're asked for a sample, it's n equals question mark. Would you need to be 90% confident? Okay, and 90%, if we look that up on the chart, we get 1.645. That the mean diameter is, okay, so here's the interval, 7.53 plus or minus 0.01. Okay, so if we actually did 7.53 plus or minus 0.01, what that would equate to is, if you think about it, it would be 7.52 to 7.54. Okay, so how large of a sample? Let's just change colors right now. Okay, let's go n equals, and let's just sub right in, okay? 2, and then the z, 2, 1.654. And then sigma, which is 0.1, all over w, which in this case is 0.02. Okay, 0.02. Okay, and when you calculate that, you get approximately 271. So you would need to sample, or 271 bolts, in order to be 90% confident that the mean diameter is in this interval. Okay, and just to point out, this W, this is the margin of error, okay? So margin of error is the entire margin. So we know that half the margin for this one is 0.01. So then the entire margin of error is going to be 0.02. And that's where we get that denominator from, okay? Just to make that point.